Right now, at this very moment, beneath your feet, something extraordinary is happening so slowly that in your entire lifetime, you'll never notice it. The ground you're resting on, the mountains in the distance, the very continents themselves, they're all dancing, drifting across the surface of our planet like massive, ancient ships on an ocean of molten rock. Welcome to Sleep About Science. Tonight, wherever you are in the world, we're exploring how mountains move through time. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, there's something rather poetic about falling asleep while learning about the Earth's own slow, eternal slumber and awakening cycles. Before we begin, please make yourself comfortable. Pull up your blankets, adjust your pillow, let your body sink into whatever soft surface is supporting you right now. And remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into science. There's something deeply soothing about understanding the slow, patient rhythms of our planet. Now imagine for a moment that you could speed up time, not just a little, but dramatically, so dramatically that you could watch the Earth as it truly is, a living, breathing, constantly changing world where mountains rise like slow motion waves, where continents drift like lazy clouds across the sky, where what seems permanent and eternal is actually fluid, dynamic, always in motion. The mountain nearest to you right now, whether you can see it from your window or whether it's hundreds of miles away, that mountain is moving. Right now, as you listen to these words, it's traveling across the Earth's surface at about the same speed your fingernails grow, which is to say, roughly 2 inches per year. In your lifetime, that mountain will move about 10 to 12 feet. Not much by our standards, but in geological time, in the patient, unhurried timeline of the Earth itself, that mountain is practically racing. But we're getting ahead of ourselves. Let's start at the beginning with a question that seems simple, but opens up into one of the most beautiful stories in all of science. How do mountains move? The answer begins deep beneath your feet, deeper than any human has ever traveled, in a realm of such heat and pressure that rock flows like honey, where the very atoms of iron and nickel swirl in patterns that generate the magnetic field protecting us from the solar wind. We're talking about the Earth's mantle, a layer of hot rock nearly 2,000 miles thick, wrapped around our planet's molten iron core like a thick, warm blanket. Now, when I say hot, I mean really hot. The temperature down there ranges from about 1,000 degrees Celsius near the top to over 3,000 degrees at the bottom. That's hot enough to melt copper, hot enough to turn sand into glass, hot enough to make rock flow like a very, very slow river. And flow it does. The mantle is constantly in motion, driven by heat from the Earth's core below and cooling from the crust above. Think of it like a pot of thick soup simmering on the stove. The hot soup at the bottom rises up, cools near the surface, then sinks back down, creating these slow, majestic circulation patterns called convection currents. But here's where it gets truly remarkable. These convection currents in the mantle don't just stay down there. They reach up and grab hold of the Earth's crust, the thin shell of rock we live on, and they drag it around like leaves on the surface of a pond. The Earth's crust isn't one solid piece, you see. It's broken up into enormous pieces called tectonic plates, like a cracked eggshell that's still holding together. There are about 15 major plates and many smaller ones, each one a massive slab of rock, anywhere from 60 to 120 miles thick. And these plates, driven by those slow currents in the mantle below, are constantly moving. Right now, as you rest there in the darkness, the North American plate, assuming you're somewhere in North America, is sliding westward at about an inch per year. If you're in Europe, you're riding on the Eurasian plate, drifting slowly eastward. If you're in Australia, your entire continent is racing northward at nearly 3 inches per year, which in geological terms is practically breakneck speed. This movement of tectonic plates, this grand slow dance of continents, is what we call plate tectonics, and it's one of the most important discoveries in the history of science, even though the idea is less than a century old. For most of human history, people assumed that mountains and continents were permanent, unchanging, eternal. The ancient Greeks thought the earth was fundamentally static. Medieval scholars believed that God had created the continents in their current positions and that they would remain there until the end of time. Even as late as the early 1900s, most scientists thought that while the Earth's surface might change through erosion and volcanism, the basic arrangement of continents and oceans was fixed. But then, in 1912, a German meteorologist named Alfred Wegener noticed something curious. Looking at maps of the world, he saw that the coastlines of different continents seemed to fit together like pieces of a jigsaw puzzle. The east coast of South America, for instance, seemed to match almost perfectly with the west coast of Africa, not just roughly, but with remarkable precision, as if they had once been joined together and then somehow pulled apart. Jenner proposed a radical idea that all the continents had once been part of a single massive supercontinent that he called Pangaea, meaning all Earth in ancient Greek. This supercontinent, he suggested, had broken apart over millions of years, with the pieces drifting across the globe to their current positions. The idea was revolutionary, and most scientists at the time rejected it completely. How could something as massive as a continent possibly move? What force could be powerful enough to push entire land masses across thousands of miles of ocean? Jenner couldn't answer these questions, and without a mechanism to explain continental drift, his theory was largely dismissed. It would be another 50 years before scientists discovered the answer, hidden beneath the world's oceans in places so remote and extreme that no human had ever seen them directly. Picture this: you're in a submarine, descending through the pitch black depths of the Atlantic Ocean. You're going down, 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 past where sunlight can reach, past where any surface waves can be felt, into a world of eternal darkness and crushing pressure. You're heading for the ocean floor, more than 2 miles below the surface. And there, stretching across the bottom of the ocean like a massive underwater mountain range, you discover something extraordinary: the Mid Atlantic Ridge, a chain of underwater mountains that runs right down the middle of the Atlantic Ocean from north to south, like a seam on a baseball. But this isn't just any mountain range. This is a place where the earth is quite literally tearing itself apart. Along the crest of this ridge, new ocean floor is being born. Molten rock from deep within the earth rises up through cracks in the ocean floor, cools into solid rock, and gets pushed aside to make room for more new rock behind it. It's like a conveyor belt of stone, constantly creating new seafloor and pushing the older seafloor further and further away from the ridge. This process, called seafloor spreading, was discovered in the 1960s, and it finally provided the mechanism that Wegener had been missing. The ocean floors aren't permanent. They're constantly being created at mid-ocean ridges and destroyed at deep ocean trenches, where old seafloor slides back down into the mantle to be melted and recycled. And this movement of the seafloor is what drives the movement of continents. The continents don't plow through the oceans like ships through water. Instead, they ride on top of the moving ocean floor like passengers on a slowly moving walkway. Now, you might be wondering, if new ocean floor is constantly being created, why aren't the oceans getting bigger? The answer is beautifully elegant. At the same rate that new seafloor is being created at mid-ocean ridges, old seafloor is being destroyed at subduction zones, places where one tectonic plate slides beneath another and disappears back into the mantle. Imagine two conveyor belts meeting head-on. One brings new material up from below, the other takes old material back down. The surface area stays the same, but the material is constantly cycling, constantly renewing itself. And it's at these collision zones, between tectonic plates, these subduction zones, and continental collision zones, where mountains are born. Let's journey now to the most spectacular example of mountain building on our planet, the Himalayas. These magnificent peaks, including Mount Everest, the highest point on Earth, are the result of one of the most dramatic geological events in our planet's recent history. About 50 million years ago, which is recent by geological standards, there was no Himalayan mountain range. Instead, there was an ocean called the Tethys Sea, stretching between two continents, Eurasia in the north and a smaller landmass in the south that we now call India. But India wasn't where it is today. It was much further south, part of the ancient supercontinent Gondwana, which was slowly breaking apart. And India, riding on its own tectonic plate, was moving north. Not quickly by our standards, only about 6 inches per year, but steadily, relentlessly, like a massive geological freight train heading for a collision. For millions upon millions of years, India crept northward across the Tethys Sea. The ocean floor between India and Eurasia was being consumed at subduction zones, disappearing back into the Earth's mantle. The ocean was shrinking, and the two continents were getting closer and closer together. And then, about 40 to 50 million years ago, they collided. Now, when two cars collide, one or both of them crumples, but when two continents collide, something far more spectacular happens. Continental crust is too light, too buoyant to sink back into the mantle the way oceanic crust does. So when India slammed into Eurasia, neither continent could subduct beneath the other. Instead, the edges of both continents crumpled upward like two pieces of paper being pushed together from opposite sides. The result was the Himalayas, a mountain range so tall and so vast that it fundamentally changed the climate of our entire planet. The collision between India and Eurasia created peaks so high that they pierced the jet stream, so massive that they block the flow of air masses across Asia, creating the monsoon systems that bring life-giving rain to billions of people. And here's the truly remarkable thing. This collision is still happening. India is still pushing northward into Eurasia at about 2 inches per year. The Himalayas are still growing, still being pushed higher by the relentless pressure of continental collision. Mount Everest gains about 4 millimeters of height every year, not much by our standards, but in geological time, it's like watching a mountain race toward the sky. But the Himalayas are just one example of how mountains move through time. There are many different ways that mountains can be born, grow, travel, and eventually fade away. Each type tells its own story about the restless energy of our planet. Consider the Andes Mountains of South America's the longest mountain range on Earth, stretching over 4,000 miles from north to south along the western edge of the continent. The Andes were born not from continental collision, but from subduction, the process where oceanic crust slides beneath continental crust and disappears into the mantle. Off the western coast of South America, the Nazca Plate, a piece of Pacific Ocean floor, is sliding eastward beneath the South American plate at about 3 inches per year. As this oceanic crust descends into the hot mantle, it releases water and other volatile compounds that lower the melting point of the surrounding rock. This creates magma molten rock that rises up through the continental crust above, creating volcanoes and pushing up mountain ranges. The Andes are still growing, still being pushed higher by this ongoing subduction. The earthquakes that occasionally shake Peru, Chile, and Ecuador are reminders that this process is still active, still reshaping the landscape. Then there are mountains, like those in the Basin and Range Province of the western United States, places like Nevada and parts of California, Utah, and Arizona. Here, the crust isn't being compressed and pushed upward. Instead, it's being stretched apart, like taffy being pulled from both ends. As the crust stretches, it breaks along fault lines, creating a landscape of parallel mountain ranges and valleys. Some blocks of crust drop down to form valleys, while others remain high to form mountains. It's like a series of dominoes, but instead of falling over, they're tilting and sliding past each other in slow motion. This type of mountain building creates a distinctive landscape, long linear mountain ranges separated by flat valleys, all running roughly north to south. The mountains in Nevada, with their stark beauty and dramatic profiles, are the result of millions of years of this stretching and faulting. And then there are the volcanic mountains, peaks like Mount Fuji in Japan, Mount Rainier in Washington, or Kilauea in Hawaii. These mountains are built not by the collision or stretching of tectonic plates, but by the accumulation of volcanic material over time. Some volcanic mountains, like those in the Cascade Range of the Pacific Northwest, are formed by subduction, the same process that creates the Andes. As oceanic crust slides beneath continental crust, it creates magma that rises to the surface, building volcanoes one eruption at a time. Other volcanic mountains, like those in Hawaii, are formed by hot spots, plumes of hot material that rise from deep in the mantle and punch through the overlying tectonic plate like a welding torch through metal. The Hawaiian Islands are actually the tops of massive volcanoes that have been built up from the ocean floor by millions of years of eruptions. But here's what's truly fascinating about Hawaiian volcanoes. They're not stationary. The hotspot that creates them stays in roughly the same place, but the Pacific plate above it is constantly moving northwest at about 3 inches per year. So over time, the hotspot creates a chain of volcanoes, with new ones forming over the hotspot, while older ones are carried away by the moving plate. This is why the big island of Hawaii, with its active volcanoes, is at the southeastern end of the Hawaiian chain, while the older dormant islands stretch away to the northwest. Each island in the chain was once positioned over the hotspot, had its time as an active volcano, and then was carried away by plate motion to make room for the next island to form. The Hawaiian chain actually extends much further than most people realize. The older islands have been eroded down to sea level and beyond, but they're still there as underwater seamounts. The entire Hawaiian Emperor Seamount chain stretches for more than 3,600 miles across the Pacific, recording 80 million years of hotspot volcanism and plate motion. Now, you might be wondering if mountains are constantly being pushed up by tectonic forces. Why isn't the Earth just one giant mountain range by now? Why are there still valleys and plains and gentle hills? The answer is that while tectonic forces are pushing mountains up, other forces are constantly wearing them down. The moment a mountain begins to rise above sea level, it comes under attack from erosion, the slow but relentless process by which wind, water, ice, and gravity wear down even the hardest rock. Rain falls on mountain peaks and seeps into cracks in the rock. When that water freezes, it expands, wedging the cracks wider until pieces of rock break off. Rivers carve deep valleys through mountain ranges, carrying away millions of tons of sediment every year. Glaciers grind down mountainsides like massive sandpaper, sculpting peaks and valleys with patient, unstoppable force. The Appalachian Mountains of eastern North America are a perfect example of this ongoing battle between uplift and erosion. These mountains were once as tall as the Himalayas are today, pushed up by continental collisions that occurred hundreds of millions of years ago. But they've been subjected to erosion for so long that they've been worn down to gentle, rounded peaks covered in forest. Yet even the Appalachians are still moving, still changing. Recent measurements using GPS satellites have shown that parts of the Appalachian Mountains are actually rising very slowly, not because new tectonic forces are pushing them up, but because they're still rebounding from the weight of ice sheets that covered them during the last ice age. During the ice ages, massive glaciers, thousands of feet thick, covered much of North America and Europe. The weight of all that ice was so enormous that it actually pressed the Earth's crust downward, like pushing down on a foam mattress. When the ice melted about 10,000 years ago, the crust began to slowly rebound, rising back up to its original position. This process, called post-glacial rebound or isostatic rebound, is still happening today. Parts of Canada and Scandinavia are rising by about half an inch per year as the crust continues to recover from the weight of the ice sheets. It's like a slow motion movie of a mattress returning to its original shape after a heavy weight has been removed. But let's zoom out now from individual mountain ranges and consider the bigger picture, the grand dance of continents across deep time. Mountains don't just move by growing taller or being worn down by erosion. They literally travel across the surface of the earth as passengers on the moving tectonic plates. The Appalachian Mountains, for instance, haven't always been in eastern North America. When they first formed, about 300 to 400 million years ago, they were located much further south, closer to the equator. North America itself has been drifting northward and rotating clockwise for hundreds of millions of years, carrying the Appalachians along for the ride. In fact, if you could travel back in time 300 million years, you would find parts of what is now the eastern United States located in the southern hemisphere, with a tropical climate complete with coal swamps and primitive forests. The coal deposits of Pennsylvania and West Virginia are the compressed remains of those ancient tropical forests now located thousands of miles north of where they originally formed. This movement of continents and mountain ranges across the globe has profound implications for climate and life on Earth. When continents are clustered together in supercontinents like Pangaea, ocean currents are disrupted, climates become more extreme, and ice ages are more likely. When continents are spread out, as they are today, ocean currents can circulate more freely, moderating global temperatures. The position of mountain ranges also affects climate patterns. The Himalayas, for instance, block cold Arctic air from reaching the Indian subcontinent, helping to maintain the warm climate that supports over 1 billion people. At the same time, they force moisture laden air masses to rise and cool, creating the heavy rainfall of the monsoon seasons. As the Himalayas continue to grow, and as India continues to push northward, these climate patterns will slowly change over millions of years. The mountains will get taller, the monsoons may become stronger or weaker, and the entire climate system of Asia will gradually evolve. But the movement of mountains through time isn't just about the present and future. It's also about deep time, the vast stretches of Earth's history that preceded human existence. By studying ancient mountain ranges, geologists can reconstruct the positions of ancient continents and understand how our planet has changed over billions of years. The oldest mountain ranges on Earth are found in places like the Canadian Shield, parts of Australia, and southern Africa. These ancient mountain belts, called cratons, formed more than 2.5 billion years ago when the Earth was a very different place. The atmosphere contained almost no oxygen. Life existed only as single celled organisms in the oceans, and the day was only about 18 hours long because the moon was much closer to Earth. These ancient mountains have been worn down almost completely by billions of years of erosion, but their roots remain embedded in the continental crust like the foundations of long demolished buildings. By studying the rocks and minerals in these ancient mountain belts, geologists can piece together the story of how continents first formed and how plate tectonics began on our planet. One of the most remarkable discoveries in recent decades is that some of these ancient mountain belts can be matched across different continents, providing evidence that continents that are now separated by thousands of miles of ocean were once joined together. The Appalachian Mountains of North America, for instance, are part of the same ancient mountain belt as the Caledonides of Scotland and Scandinavia. When you hike through the mountains of New Hampshire or Vermont, you're walking on rocks that were once continuous with the highlands of Scotland, separated only when the Atlantic Ocean began to form about 200 million years ago. Similarly, mountain ranges in South America match up with ranges in Africa. Mountains in Antarctica match up with ranges in Australia and India, and mountain ranges in eastern Australia match up with ranges in western North America. It's as if the Earth's mountain ranges are part of a giant planetary jigsaw puzzle that has been taken apart and scattered across the globe by continental drift. This matching of ancient mountain belts across modern oceans is some of the strongest evidence we have for plate tectonics and continental drift. The mountains themselves are witnesses to Earth's deep history, recording in their rocks the story of ancient supercontinents and the slow dance of continents across geological time. But mountains don't just record the past, and they also give us glimpses of the future. By understanding how mountains move and change over time, scientists can make predictions about how our planet will continue to evolve over the next hundreds of millions of years. The Atlantic Ocean, for instance, is still growing wider as new seafloor is created at the mid Atlantic ridge. Europe and North America are moving apart at about an inch per year, so in 100 million years, the Atlantic will be significantly wider than it is today. New York and London, already separated by about 3,400 miles, will be about 1,600 miles further apart. Meanwhile, the Pacific Ocean is shrinking as its edges are consumed by subduction zones. The Pacific Plate is diving beneath the North American Plate along the west coast of North America, beneath the South American Plate along the west coast of South America, and beneath the Eurasian and Philippine plates along the western Pacific. In about 200 to 300 million years, the Pacific Ocean may close completely, bringing Asia and North America into direct contact. Australia is racing northward toward Asia at nearly 3 inches per year. In about 50 million years, Australia will collide with Southeast Asia, creating a new mountain range that may rival the Himalayas in scale and grandeur. Indonesia, with its thousands of islands, will be compressed and uplifted into a continuous landmass. Africa is also moving northward, slowly closing the Mediterranean Sea. In about 50 million years, Africa will collide with Europe, eliminating the Mediterranean entirely and creating a new mountain range stretching from Spain to Turkey. The Alps, already formed by the early stages of this collision, will be dwarfed by the new range. Even more dramatically, the East African Rift Valley, place where the African continent is slowly tearing itself apart, may eventually split Africa into two separate continents. The rift is growing wider at about half an inch per year, and in 10 to 50 million years, the eastern part of Africa, including parts of Kenya, Tanzania, and Ethiopia, may become a separate continent separated from the rest of Africa by a new ocean. These future changes seem almost impossibly slow by human standards, but they're happening at the same steady pace that has shaped our planet for billions of years. The mountains you can see from your window tonight will be in completely different locations millions of years from now, carried along by the patient, inexorable movement of tectonic plates. But let's bring this back to a more human scale, to something you can actually observe in your lifetime. While you won't see continents drift or mountains grow significantly taller, you can witness the effects of mountain movement in more subtle ways. Earthquakes, for instance, are direct evidence of mountains and tectonic plates in motion. Every earthquake is caused by the sudden release of stress that has been building up as tectonic plates push against each other, slide past each other, or pull away from each other. The rocks along fault lines bend and strain like rubber bands until they suddenly snap back to their original shape, sending seismic waves racing across the Earth's surface. The famous San Andreas Fault in California is a place where you can actually see this movement happening in real time. The Pacific Plate, carrying Los Angeles and the southern part of California, is sliding northwest past the North American Plate, carrying San Francisco and the northern part of California at about 2 inches per year. Over millions of years, this movement has carried rocks that originally formed near Mexico hundreds of miles to the north. Distinctive rock formations can be traced along the fault, showing how the landscape has been sliced and shifted by this ongoing plate motion. In about 10 million years, Los Angeles will be at the same latitude as San Francisco. In 50 million years, it will be sliding past the Oregon coast. You can also see evidence of mountain movement in the slow uplift and tilting of coastlines. In many places around the world, Ancient beaches and coral reefs can be found high above current sea level, lifted up by the slow rise of tectonic plates. Marine fossils, the remains of creatures that lived in ancient seas, can be found in mountain ranges thousands of feet above sea level, carried upward by the same forces that build mountains. Conversely, in some places, coastlines are slowly sinking as tectonic plates subduct, or as the weight of sediment causes the crust to sag. Venice, Italy, is sinking partly because of the weight of the city itself and partly because of larger tectonic movements. Many coastal cities around the world are dealing with the effects of both sea level rise and land subsidence, the slow sinking of the land surface. Even the magnetic field of the Earth records the movement of mountains and continents through time. As rocks form and cool, they lock in the direction of the Earth's magnetic field at the time and place they solidified. By studying the magnetic orientations preserved in ancient rocks, scientists can determine not only where those rocks formed, but also how they've moved and rotated since then. This technique, called paleomagnetism, has revealed that many mountain ranges have traveled thousands of miles from their original locations and have rotated significantly as they moved. Some mountain ranges in the western United States, for instance, have rotated more than 90 degrees clockwise since they formed, like compass needles that have spun around as they traveled. The movement of mountains through time is also intimately connected with the evolution of life on Earth. Mountain ranges create barriers that separate populations of plants and animals, leading to the evolution of new species on either side of the divide. The rise of the Himalayas, for instance, separated the flora and fauna of India from those of the rest of Asia, leading to the unique biodiversity we see in the Indian subcontinent today. Conversely, when mountain ranges are worn down by erosion or when continents drift together, previously separated populations can mix and interact, leading to new evolutionary pressures and opportunities. The formation and destruction of mountain ranges over geological time has been one of the major drivers of biodiversity on our planet. Mountains also affect the evolution of climate over deep time. When large mountain ranges form, they can alter global patterns of wind and precipitation, leading to the expansion of deserts on one side and the development of rainforests on the other. The rise of the Himalayas and the Tibetan Plateau intensified the Asian monsoon system and may have contributed to global cooling over the past 50 million years by increasing the rate at which carbon dioxide is removed from the atmosphere through the weathering of rocks. As mountains are uplifted, fresh rock is exposed to the atmosphere and begins to weather chemically. This weathering process consumes carbon dioxide from the atmosphere, helping to regulate Earth's climate over long timescales. Some scientists believe that the rapid uplift of the Himalayas and other mountain ranges over the past 50 million years has contributed to the long-term cooling trend that led to the ice ages of the past few million years. The movement of mountains through time is in essence the heartbeat of our planet, the slow, steady rhythm of geological processes that have shaped the Earth for billions of years. It's a reminder that what seems permanent and unchanging in our brief human lifespans is actually dynamic and fluid over the vast timescales of Earth's history. As you rest there in the darkness tonight, perhaps you can feel a different kind of connection to the earth beneath you. You're not just lying on solid, unchanging ground, you're riding on a massive tectonic plate that's carrying you across the surface of the planet at a few inches per year. You're part of the same grand, slow dance of continents and mountains that has been going on for billions of years and will continue for billions more. The mountain ranges visible from your location, whether they're the Rockies, the Alps, the Andes, or any other peaks, are not permanent fixtures of the landscape. They're temporary sculptures, carved by the interplay of tectonic forces and erosion, constantly changing as the earth reshapes itself. In the deep future, they'll be worn down to gentle hills or carried to entirely different parts of the planet, while new mountain ranges rise from the sea floor or from the collision of continents yet to come. There's something deeply comforting about this perspective, the idea that the earth itself is alive, constantly changing and renewing itself. The mountains that seem so solid and eternal are actually flowing like slow rivers of stone, rising and falling in rhythms, so patient that they make human history seem like a brief flicker. Yet at the same time, there's something humbling about it. All of human civilization, all of our cities and roads and monuments exists on the surface of a planet that's constantly in motion, constantly reshaping itself according to forces and timescales that dwarf our everyday experience. The ground beneath our feet is not the stable foundation we imagine it to be, but rather the surface of a dynamic, ever changing world. But perhaps that's what makes it all the more precious. The temporary nature of mountains, continents, and indeed our entire planetary configuration makes each moment, each landscape, each mountain vista something to be treasured. The peaks you can see from your window tonight are here now in this configuration at this moment in Earth's long history. Millions of years from now, they'll be somewhere else entirely, worn down and rebuilt, carrying with them the slow memory of tectonic forces and deep time. And you're here to witness it, to be conscious of this grand planetary dance, to understand something of how mountains move through time. In the 4.5 billion year history of the Earth, conscious beings capable of understanding plate tectonics have existed for less than the blink of an eye. You're part of a brief but remarkable moment when the Earth has developed the ability to contemplate its own geology, to marvel at its own slow transformations. Scientists estimate that complex life capable of leaving fossils and eventually evolving into conscious beings, has existed for only about 540 million years, roughly 12% of Earth's history. Complex consciousness, capable of understanding plate tectonics, has existed for perhaps the last few centuries, less than 0.0000001% of Earth's history. You're living in an extraordinarily special time when a planet has become aware of its own geological processes. The mountains around you have been moving through deep time long before consciousness existed to observe them, and they'll continue moving long after consciousness disappears. But right now, in this brief moment, you have the remarkable privilege of understanding something about how they work boob, of being a temporary observer of an ancient and ongoing process. As we near the end of our journey tonight, let's return to that image we started with idea of speeding up time to see the earth as it truly is. If you could watch the last 500 million years compressed into a few minutes, you would see something like a slow motion dance of continents and mountains, with land masses drifting across the globe like pieces on a vast chessboard. You would see the supercontinent Pangaea slowly breaking apart, with pieces drifting in different directions like fragments from a cosmic explosion. You would watch the Atlantic Ocean opening like a slowly unfolding flower, pushing Europe and North America apart while new seafloor spreads between them. You would see India's epic journey from the southern hemisphere to its collision with Asia, creating the Himalayas in a slow motion crash that's still happening today. You would watch Australia break away from Antarctica and race northward toward its future collision with Southeast Asia. You would see mountain ranges rise and fall like slow waves, growing tall through tectonic compression and then being worn down by millions of years of erosion. You would see volcanic arcs sweep across the Pacific as oceanic plates carry island chains away from their hotspot sources. And through it all, you would see the constant recycling of the ocean floor, new seafloor being created at mid ocean ridges, while old seafloor disappears into subduction zones, like a planetary scale conveyor belt that has been running for billions of years. This dance is still happening now, even as you rest there in the quietness of the night. The mountains around you are moving, growing, changing. The continent you're on is drifting across the Earth's surface, deep beneath your feet. Convection currents in the mantle are slowly stirring, driving the great machine of plate tectonics that shapes our world. It's a process so slow that it's essentially invisible to us, yet so powerful that it has shaped every aspect of our planet: the distribution of land and sea, the location of mountain ranges and river valleys, the patterns of climate and weather, even the evolution and distribution of life itself. In our daily lives, we rarely think about these deep geological processes. We experience the earth as solid, stable, unchanging. We build our cities and plant our crops as if the landscape will remain the same forever. But now you know the deeper truth that the earth is a dynamic, restless planet where nothing is truly permanent except change itself. The mountains move through time, carrying with them the patient memory of tectonic forces and deep history. They rise from the sea floor as volcanic islands, grow tall through continental collision, travel across the globe as passengers on drifting plates, and eventually are worn down by erosion and carried back to the sea as sediment, only to be recycled into new mountains millions of years later. It's a cycle that has been repeating for billions of years, long before life existed on Earth, and it will continue for billions of years after our sun expands into a red giant and makes our planet uninhabitable. The mountains will keep moving, the continents will keep drifting, the ocean floor will keep spreading and recycling, driven by the heat engine in the Earth's interior that shows no signs of slowing down. But tonight, in this moment, you have the privilege of understanding something about this grand process. You can look at the mountains around you, whether they're visible from your window or exist only in your imagination, and know that they're not the permanent, unchanging features they appear to be. They're travelers in time, passengers on a journey that began billions of years ago and will continue long into the unimaginable future. And perhaps there's a kind of peace in this knowledge, the understanding that you're part of something much larger and older and more patient than human civilization. The rhythms of your daily life, with their urgencies and deadlines and immediate concerns, are nested within the much slower rhythms of geological time, where mountains rise and fall like breathing, where continents drift like clouds, where the very surface of the earth flows and changes like a slowly moving river. There's something deeply soothing about contemplating these vast time scales, your worries, your stress, your immediate concerns, they're all real and important, but they exist within the context of a planet that operates on timescales so vast that they put human troubles into a different kind of perspective. The mountain nearest to you has been dealing with forces that would crush any human structure, yet it endures, changes, adapts, moves through time with patient grace. Consider the journey of a single grain of sand, perhaps one that's resting right now on a beach somewhere in the world, or embedded in the sandstone of a desert cliff, or mixed into the concrete foundation of a building. That grain of sand began its journey millions or even billions of years ago as part of a mountain range that may no longer exist. Perhaps it started as part of a granite peak in an ancient mountain range, maybe the roots of mountains that were old when dinosaurs walked the girth. Over millions of years, that mountain was slowly worn down by wind and rain and ice. Our grain of sand was freed from its crystalline prison and began a journey that might have taken it through dozens of different environments. It might have been carried by rivers to the sea, where it settled on the ocean floor and was compressed into sandstone. That sandstone might have been uplifted in a later mountain building episode, exposed to erosion again, and freed once more to continue its journey. It might have been buried under other sediments, heated and pressurized until it became part of a metamorphic rock, then uplifted and eroded again. Through all of these transformations, our grain of sand is a traveler through deep time, a witness to the slow dance of mountains and continents. It has seen mountain ranges rise and fall, seen continents drift across the globe, seen the climate change from ice age to greenhouse and back again. And now, for this brief moment in geological time, it rests wherever it happens to be, waiting for the next phase of its epic journey. Every grain of sand, every pebble on the beach, every rock in your garden has a similar story and biography written in stone that spans millions or billions of years. They are all fragments of ancient mountains, pieces of the Earth's long history of uplift and erosion, construction and destruction, the endless recycling of rock through the grand cycles of geological time. And this recycling extends far beyond individual grains of sand or pebbles. Entire mountain ranges are recycled over geological time. The Himalayas, for instance, are not just being pushed up by the collision between India and Asia, they're also being worn down by erosion. Every year, the rivers flowing out of the Himalayas carry millions of tons of sediment to the sea. This sediment doesn't just disappear, it accumulates on the ocean floor, where it may eventually be compressed into new sedimentary rocks. Those rocks may be uplifted in future episodes of mountain building, creating new mountain ranges from the debris of old ones. In this sense, mountains are not just moving through space as they ride on tectonic plates, they're also moving through the rock cycle, constantly being torn down and rebuilt from their own remains. The Ganges River, flowing out of the Himalayas, carries so much sediment that it has built an enormous fan of deposited material called the Bengal fan that extends for more than 1,800 miles across the floor of the Indian Ocean. This fan contains the eroded remains of Himalayan peaks spread out across the ocean floor in layers that record millions of years of mountain building and erosion. Someday, perhaps hundreds of millions of years from now, the sediment may be uplifted again as tectonic plates shift and collide. The rocks that now form the peaks of Mount Everest may in the distant future be worn down to sand grains resting on some future ocean floor. And the sediment that now lies on the floor of the Indian Ocean may be uplifted to form the peaks of some future mountain range, completing a cycle that spans hundreds of millions of years. This is the deeper meaning of how mountains move through time. They don't just travel across the surface of the earth, they travel through cycles of creation and destruction that operate on timescales almost too vast to comprehend. They are born from the collision of continents, grow tall through tectonic compression, travel across the globe as passengers on moving plates, are worn down by erosion, and are eventually recycled into new mountains in an endless cycle that has been operating for billions of years. But let's zoom in now from these vast timescales to something more immediate, more connected to human experience. While you'll never see continents drift or mountains grow significantly taller in your lifetime, you can witness the effects of these processes in ways that connect you directly to the deep history of the Earth. Every time you see a landslide on a mountain slope, you're witnessing erosion in action, the same process that has been wearing down mountains for billions of years. Every time you see a river cutting through a valley, you're seeing the patient work of water carving through rock, the same force that has shaped mountain ranges throughout Earth's history. When you pick up a smooth river rock, you're holding something that has been tumbled and shaped by the same forces that wear down mountains. That rock may have started as part of a mountain peak hundreds of miles away and hundreds of thousands of years ago, broken free by frost and carried downstream by countless floods, slowly worn smooth by its long journey. When you see layers of rock exposed in a road cut through a mountain, you're looking at pages in the Earth's autobiography, layers of sediment that were deposited over millions of years, then uplifted and tilted and folded by the same tectonic forces that build mountains. Each layer tells a story of ancient environments, seas that covered the land, deserts that left their sand dunes preserved in stone, rivers that meandered across ancient floodplains. These rock layers are like tree rings, but instead of recording years, they record millions of years. And they don't just record time, but they record motion. Layers that were originally horizontal have been tilted and folded, showing how the Earth's crust has been compressed and deformed by tectonic forces. Layers that were once at the bottom of ancient seas are now at the tops of mountains, lifted up by the slow but inexorable process of mountain building. In some places, you can see this history written dramatically in the landscape. The Grand Canyon, for instance, is like a book open to show its pages, layers of rock representing nearly 2 billion years of Earth's history, each layer telling a different chapter in the story of ancient environments and changing climates. But the Grand Canyon also tells a story of motion, not just the motion of the Colorado River cutting downward through the rock, but the motion of the entire Colorado Plateau being lifted up by tectonic forces. The canyon exists because the land was raised faster than the river could adjust its course, forcing the river to cut down through solid rock to maintain its path to the sea. This is happening in mountains all over the world. Rivers cutting through rising mountains, creating deep gorges and dramatic valleys as they race to keep up with tectonic uplift. The rivers are not just passive agents of erosion, they're active participants in a contest between the forces that build mountains and the forces that tear them down. And this contest is not just happening in dramatic places like the Grand Canyon or the Himalayas. It's happening everywhere, even in the gentlest landscapes. Every hill in your local area, every small stream, every valley is part of this ongoing conversation between uplift and erosion, between the forces that build up the land and the forces that wear it down. The rolling hills of the English countryside, the gentle ridges of the eastern United States, the subtle undulations of the Great Plains, all of these landscapes bear the signature of ancient mountain building episodes, now softened and subdued by millions of years of erosion. They are the ghosts of ancient mountains, the worn down remnants of ranges that once stood as tall as the Alps or the Rockies. Even in places that seem completely flat, the story of moving mountains is written in the rock beneath the surface. The Great Plains of North America, for instance, appear almost perfectly level, but beneath the grass and soil lie thousands of feet of sediment eroded from the Rocky Mountains and carried eastward by ancient rivers over millions of years. This sediment didn't just accumulate randomly, it was deposited in layers that record the rise and fall of the Rockies over geological time. When the mountains were growing rapidly, more sediment was eroded and carried to the plains. When mountain building slowed, less sediment was deposited. The thickness and composition of these sediment layers tell a detailed story of how the Rocky Mountains have moved through time, and this story is still being written. Every year, rivers flowing eastward from the Rockies carry millions of tons of sediment toward the Great Plains and eventually to the Gulf of Mexico. The Mississippi River Delta is built from sediment eroded from mountains all across the western United States, the Rockies, the Appalachians, and everything in between. This sediment doesn't just disappear into the ocean. It accumulates on the seafloor where it may eventually be compressed into new sedimentary rocks. And if future tectonic movements should cause this part of the ocean floor to be uplifted, these rocks formed from the eroded remains of today's mountains may become the building blocks of future mountain ranges. It's a cycle within a cycle, the rock cycle nested within the larger cycle of plate tectonics. Mountains are built from the debris of older mountains, which were themselves built from the debris of even older mountains, stretching back through billions of years of Earth's history. But the movement of mountains through time is not just a mechanical process of rocks being uplifted and eroded, it's also a biological process intimately connected with the evolution and distribution of life on Earth. Mountains create unique environments, places where temperature, precipitation, atmospheric pressure, and soil conditions are different from the surrounding lowlands. These mountain environments become refugia for life, places where species can evolve in isolation and develop unique adaptations to high altitude conditions. The movement of mountains through time has been one of the major drivers of biological evolution. When mountain ranges rise, they create barriers that separate populations of plants and animals, allowing them to evolve independently on either side of the divide. When mountain ranges are worn down, these barriers disappear, allowing previously separated populations to mix and interact. The rise of the Himalayas, for instance, created a massive barrier between the Indian subcontinent and the rest of Asia, allowing the unique flora and fauna of India to evolve in relative isolation. The plants and animals of the Western Ghats, an ancient mountain range along India's western coast, include many species found nowhere else on Earth, evolutionary relics that have survived in these mountain refugia for millions of years. Similarly, the rise of the Andes created unique high-altitude environments that supported the evolution of specialized plants and animals adapted to thin air, intense ultraviolet radiation, and extreme temperature fluctuations. The vicuñas, alpacas, and other camelids of the high Andes evolved from ancestors that lived at sea level, developing specialized blood chemistry and lung capacity to survive in the oxygen poor environment of high altitudes. When mountains move either by being carried to new latitudes by plate tectonics or by growing taller through tectonic uplift, they carry their biological communities with them. Ancient tropical forests may find themselves in temperate latitudes, while Arctic communities may be carried toward the equator. This biological hitchhiking has left its signature in the fossil record and in the distribution of modern species. Related species of plants and animals can be found on continents that are now separated by thousands of miles of ocean, evidence that these continents were once joined together when their common ancestors. The movement of mountains through time has also been intimately connected with the evolution of Earth's atmosphere and climate. Mountain ranges affect global patterns of wind and precipitation, creating rain shadows on their leeward sides and causing moisture laden air to rise and cool on their windward sides. When large mountain ranges form, they can fundamentally alter global climate patterns. The rise of the Himalayas and the Tibetan Plateau, for instance, intensified the Asian monsoon system and may have contributed to the onset of ice ages by altering global atmospheric circulation patterns. Mountains also affect climate through their influence on the carbon cycle. When fresh rock is exposed by mountain building, it begins to weather chemically, consuming carbon dioxide from the atmosphere in the process. This weathering acts as a global thermostat, helping to regulate Earth's temperature over long timescales. During periods of rapid mountain building, increased weathering removes more carbon dioxide from the atmosphere, leading to global cooling. During periods when mountain building slows and erosion dominates, less fresh rock is exposed, weathering slows, and atmospheric carbon dioxide levels may rise, leading to global warming. The movement of mountains through time is thus intimately connected with the long term evolution of Earth's climate system. Mountains are not just passive features of the landscape, they are active participants in the complex web of interactions between the solid Earth, the atmosphere, the oceans, and the biosphere. As you lie there in the darkness tonight, breathing the air that has been shaped by millions of years of mountain weathering, perhaps you can sense this deep connection between yourself and the moving mountains around you. The oxygen you breathe was freed from ancient rocks by the slow process of chemical weathering. The carbon dioxide you exhale will eventually be consumed by the weathering of fresh rock exposed by ongoing mountain building. You are part of the same planetary system that moves mountains through time ants, a system of interconnected cycles that operate on timescales from seconds to billions of years. Your breathing is synchronized with the breathing of the planet itself, the slow inhalation and exhalation of gases that connects the atmosphere with the solid earth through the weathering of mountains. And perhaps there's something profoundly peaceful about recognizing your place in these vast cycles. The anxiety and stress of daily life, the urgency of human affairs, the constant rush of modern civilization, all of these exist within the context of a planet that operates on much slower, more patient rhythms. The mountains around you have been dealing with stresses that would destroy any human construction, the crushing pressure of continental collision, the relentless grinding of glaciers, the constant assault of wind and rain and ice, yet they endure, change, adapt, flow like slow rivers of stone through the landscape of deep time. There's a kind of wisdom in mountains, the wisdom of patience, of persistence, of acceptance of change. They don't resist the forces that shape them. They respond to those forces, rising when compressed, flowing when heated, breaking when stressed beyond their limits, but always continuing, always participating in the grand dance of geological time. Mountains teach us about the deep patience required for lasting change. Human beings, with our brief lifespans and urgent needs, often want change to happen quickly. We become frustrated when progress seems slow, when solutions to problems take longer than we'd like. But mountains remind us that the most fundamental changes, the changes that reshape entire landscapes and alter the course of planetary evolution, happen slowly, gradually, with the patient accumulation of small increments over vast periods of time. A mountain grows tall, not through any single dramatic event, but through the accumulation of countless small movements. Each earthquake adding a few inches of height, each volcanic eruption adding another layer of rock, each tectonic pulse pushing the rocks a little higher. Over millions of years, these tiny increments add up to towering peaks that pierce the sky. Similarly, a mountain is worn down not through any single catastrophic event, but through the patient work of countless raindrops, each one removing a few grains of sand, each frost cycle splitting off a few more fragments of rock. Over millions of years, these tiny acts of erosion can reduce the mightiest mountain range to gentle hills. There's something deeply reassuring about this perspective, the understanding that lasting change happens gradually through the patient accumulation of small actions over long periods of time. It suggests that even the smallest efforts, if sustained over time, can have profound effects. Every grain of sand carried away by a stream, every plant root growing into a crack in the rock, every cycle of freezing and thawing these seemingly insignificant processes, repeated millions of times over millions of years, are the forces that shape mountains and move continents. And perhaps the same is true for human endeavors. The small actions we take each day, the gradual accumulation of knowledge and experience, the slow building of relationships and communities, these may seem insignificant in the moment, but over time they can reshape the landscape of human experience just as surely as geological forces reshape the physical landscape. Mountains also teach us about resilience and adaptation. They don't fight against the forces that act upon them. They respond to those forces in ways that allow them to persist and continue. When compressed, they fold and rise. When heated, they flow and reshape themselves. When broken, they heal and continue. This kind of resilience is different from the rigid resistance we sometimes think of as strength. Mountains are strong not because they're inflexible, but because they're capable of change, capable of responding to new conditions while maintaining their essential character. A mountain range may be compressed, uplifted, tilted, and eroded over millions of years, but it remains recognizably a mountain range throughout all of these transformations. It changes form while maintaining function, adapts to new circumstances, while preserving its fundamental nature. Perhaps this is a model for human resilience as well, the ability to change and adapt while maintaining our essential character, to respond to new circumstances without losing our fundamental identity. As our journey through the world of moving mountains draws toward its close, let's take a moment to appreciate the extraordinary privilege we have as conscious beings living at this particular moment in Earth's history. For the vast majority of Earth's 4.5 billion year history, mountains have moved through time without any conscious observers to witness their journey. The great dance of continents and the slow rise and fall of mountain ranges happened in perfect silence, with no minds to contemplate their meaning, no voices to tell their stories. For billions of years, mountains rose and fell in the darkness of an unconscious world. They moved across the face of the earth without any awareness of their own motion, without any understanding of the forces that drove them, without any appreciation for the beauty and complexity of their own transformations. And then, in the very recent past, just a few 100 million years ago, which is recent by geological standards, life developed the capacity to see, to think, to wonder. And eventually, after hundreds of millions more years of evolution, consciousness became sophisticated enough to understand something about the processes that shape the earth. You are living in an extraordinary moment, and time when mountains still move through deep time as they always have, but now there are conscious beings capable of understanding and appreciating their journey. You're part of a universe that has become aware of itself, a planet that has developed the capacity to contemplate its own geology. This is a privilege that's almost impossible to fully appreciate. Out of the vast reaches of space and time, you happen to exist at the one place in time we know of where consciousness has evolved sufficiently to understand plate tectonics, to trace the movement of continents through deep time, to piece together the stories told by ancient rocks. The mountains around you have been moving for billions of years without any witnesses, and they'll continue moving long after consciousness disappears from the earth. But right now, in this brief moment, you have the remarkable opportunity to be aware of their movement, to understand something about their history and their future, to participate consciously in the grand story of planetary evolution. This awareness doesn't change the mountains themselves, but it transforms their meaning. A mountain is no longer just a pile of rock shaped by blind geological forces. It becomes a chapter in a story, a character in an epic tale of planetary evolution, a participant in the grand dance of matter and energy that we call the universe. And perhaps this is the deepest meaning of how mountains move through time. Not just that they physically travel across the Earth's surface or rise and fall through geological processes, but that they move through the landscape of consciousness itself, from being mere objects to being subjects of wonder, understanding, and appreciation. As you rest there in the quietness of the night, perhaps you can feel yourself participating in this transformation. The mountains around you are the same piles of rock they were before you understood their history, but they're also somehow more than that now. They've been transformed by your awareness from static landscape features into dynamic participants in an ongoing story. This is what consciousness does. Weiner's it transforms the world from a collection of objects into a web of relationships, from a series of events into a meaningful story, from a mechanical process into something worthy of wonder and contemplation. The movement of mountains through time becomes not just a geological process, but a meditation on change, patience, resilience, and the deep connections that link all things across vast scales of space and time. It becomes a way of understanding our own place in the larger patterns of cosmic evolution, a reminder that we are not separate from the natural world, but intimately connected with it at every level. Your body is made of atoms, forged in the hearts of ancient stars, atoms that may once have been part of mountains that rose and fell long before life existed on Earth. The calcium in your bones may once have been part of ancient coral reefs, uplifted into mountain ranges, and then dissolved by weathering and carried to the sea, where it became part of the shells of marine organisms, then part of limestone, then part of your skeleton. The iron in your blood may once have been part of the Earth's molten core, brought to the surface by volcanic eruptions, oxidized by the atmosphere, weathered from ancient rocks, carried by rivers to the sea, and eventually incorporated into the bodies of tiny marine organisms that became part of the food chain that eventually led to you. You are, quite literally, made of recycled mountains. Your atoms have been on their own epic journey through deep time, participating in countless cycles of rock formation and destruction, mountain building and erosion, the endless recycling of matter that connects all things across the vast reaches of space and time. In this sense, you don't just observe the movement of mountains through time, you participate in it. You are part of the same grand process of cosmic evolution that moves continents across the Earth's surface, that builds mountain ranges from colliding plates, that wears down ancient peaks and builds new ones from their remains. The atoms in your body have been on a journey that spans billions of years and will continue for billions more. Right now, they're organized in the pattern that is you, but someday they'll be reorganized into other patterns. Perhaps part of a tree, perhaps part of the soil, perhaps part of a mountain that hasn't been born yet. This is the ultimate meaning of how mountains move through time, not just that rock moves across the Earth's surface, but that matter itself is constantly in motion, constantly being reorganized into new patterns, constantly participating in cycles of creation and destruction that connect everything with everything else across all scales of space and time. As we come to the end of our gentle journey through the world of moving mountains, perhaps you're feeling a different kind of sleepiness now, not just physical tiredness, but the deep satisfaction that comes from understanding something profound about the world around you. The mountains you can imagine from your resting place, whether they're visible from your window or exist only in your mind's eye, are no longer just static features of the landscape. They're fellow travelers on the journey through deep time, passengers like yourself on the great ship of Earth as it sails through the cosmos. They're made of the same recycled stardust that you're made of, shaped by the same fundamental forces that shape your own life, participating in the same grand story of cosmic evolution that includes everything from the smallest atom to the largest galaxy. Tonight, as you drift towards sleep, you can rest in the knowledge that you're part of something much larger and more beautiful than you might have imagined. The solid ground beneath you is not truly solid mimic. It's a dynamic flowing system of matter and energy, constantly changing, constantly moving, constantly participating in cycles of creation and destruction that span billions of years. The mountains are moving through time, and so are you. You're both part of the same grand dance, the same patient unfolding of cosmic possibility, the same beautiful story of a universe that has somehow organized itself in such a way that it can contemplate its own existence. And in contemplating the movement of mountains through time, you've participated in one of the most remarkable achievements of consciousness, the ability to understand something about the deep patterns that connect all things, to see past the apparent solidity and permanence of the world to the underlying flows and cycles that make everything possible. Sleep well tonight, knowing that you're riding on a mountain of your own, not a mountain of rock, but a mountain of organized matter that has somehow achieved the ability to think and wonder and dream. Your body, like the mountains around you, is a temporary pattern in the flow of cosmic matter and energy, a brief but beautiful organization of atoms that were once part of ancient stars and will someday be part of new worlds. The mountains will continue their slow dance across the Earth's surface long after you've returned your atoms to the cosmic recycling system. But tonight, for this brief moment in the vast expanse of time, you and the mountains are companions on the same journey, fellow participants in the grand adventure of existence itself. Thank you for joining me on this gentle exploration of how mountains move through time. Thank you for bringing your consciousness to bear on these deep patterns, for allowing wonder and understanding to transform your relationship with the landscape around you. Wherever you are in the world right now, whatever mountains are nearest to you, I hope you'll remember that they're not just piles of rock, but fellow travelers on the journey through deep time. They've been moving for billions of years, and they'll continue moving for billions more, carrying with them the patient wisdom of geological time and the quiet beauty of constant change. If you enjoyed this journey, I'd be grateful if you'd consider subscribing to Sleep About Science so we can continue exploring the gentle wonders of our universe together. And please, let me know in the comments where you're listening from tonight. I love hearing from fellow travelers around our slowly moving, constantly changing, endlessly beautiful planet. Sweet dreams, and may your sleep be as peaceful and patient as the movement of mountains through time. Good night.